Hello everyone. I hope everybody can hear me properly and well. Please let me know if the sound is bad or the image is bad. I'm kind of alone today. I don't have my son with me. Um, we had a great time in Buenos Aires. We came back. I came back a couple days yesterday, and but Ans he stayed in Buenos Aires. He's going to be there for maybe a couple months, and he's going to be doing some programming over there. He needed some space, some time to do his things. He's probably going to join us every now and then. And so during that time, next couple months or until further notice, we want to have only a couple of days where we are going to be doing transmissions. That's going to be Sundays and Wednesdays, same time, 9 o'clock Frankfurt time. What is it? I think it's 1900 hours world time, whatever it's called. Until further notice, we're going to have only twice a week because we're really behind. We got a lot of work to do, lots of videos, articles. Writing a book also. There's just too much on our plate aside from other things that force us to cut down our transmission time. And on the one hand, it's not such a bad idea to do that because it gives people time to absorb the material, discuss it for a couple days rather than go from one subject to the other from day to day. So just keep that in mind. Shamu and Dave are still there. I think they're still in Chile, stuck somewhere in Valparaiso, Chile, and I hope they're doing fine. We had a great time with them. Had a couple of reunions, meetings, discussions, whatever we want to call them, with beer and pizza and empanadas. So I think we did pretty well down there. I think we had a good time, and of course we didn't only discuss the subject matter that I covered during the presentations, which was physics. They're quite interested in this extinction issue, or we can say that they're interested in economics. Okay, and extinction. As far as I'm concerned, at least, is part of that. So we had a chance to discuss a lot of this down there. I'm sure we didn't cover the subject completely, but we did exchange ideas, and I think we understand a little better where each of us is coming from. Okay, and that's subject matter maybe for another presentation, another lecture, or whatever. So what did we cover down there? Well. I covered 3 subjects. I put one of the videos up only on the first subject. The other 2 are coming, but originally I was planning on doing polarization. Polarization is a phenomenon we've noticed with light, and I wanted to discuss that, but when I got to that point, I said, well, no, before I discuss that, I need to really discuss the slit experiment. And so let me check to see if everyone's doing fine here first here before I continue. Okay. So if there's any problem with the transmission, please let me know in the comments section. Okay, anyways, I was planning on covering polarization. And I really realized that I needed to cover the slit experiment before I did that. And then when I covered the slit experiment, I realized I had to cover physics itself, just give the groundwork for, what is physics? What is a physical interpretation? And so that's the way it went. I started with the physical interpretation. What is a physical interpretation? You'll see that video which is up there already. I've uploaded it. And then I followed that with the slit experiment and finally ended up with polarization. And that's how it went. And obviously there were a lot of questions, and that's one of the reasons, and I knew that was going to happen. So one of the reasons that I held off on the articles, of writing the articles. I did write the articles, but I didn't finish them because I waited for some feedback, and I did get some feedback, and that compels me to modify the articles to address some of those issues, questions people have. And so that's the way it went. What did I cover? And here, by the way, here's our little logo, our little commercial for the Rational Scientific Method Rational Physics Conference in Buenos Aires. I think we're going to be doing the next one somewhere in Sweden. There's a fellow who has offered to do this in Sweden or to organize it, and if he does, obviously we'll help him and we'll go down there and get it done. So the next one will probably be in Sweden. It'll probably be in summer sometime, or spring, maybe, I don't know, I would think maybe June, July, August, something like that. So just keep, if you're interested, just keep that in mind. Anyways, so what did we do? We had to cover what is a physical interpretation. And for this, you need to think in these terms that you can't do physics without an object. And so that's like the first step. If you think you can do physics without an object, well then there's nothing that we can have in common, because whatever comes next is irrelevant. So there's this principle that a rational human being, as I call them, accepts, and that's that you must have a physical object in order to do physics. Okay, some people accept that, okay, and most people I would think would accept that, but then we have a problem with the next step, and that's, what is a physical object? And I had a great discussion with another fellow who's quite interested in physics, and he's my brother, one of my brothers, and I was stunned by his answer. And so I thought I'd cover that here, because I'm going to be I have to address that in my article. I have to revise it to cover that base. And that's, he said that a physical object is that which you can measure. Now, I had heard, mass, volume, that which has mass, that which has volume, that which moves, that which you can touch, that which you can see, etc., etc. But this was the first time that someone said, no, that's an object is that which you can measure. So I got a problem with that, and it just stunned me that he would insist on that. And so I'm saying, here you have a lion, or let's put a horse, probably easier. The horse gallops, right? And the horse covers distance. Okay, it runs 1 kilometer, 1 mile, whatever. Okay, so the measurement is the distance, is how much the horse ran, or how much time he consumed to run 1 mile, or whatever. That's the measurement, how much weight the horse has, or how much mass, that kind of thing. Or how much energy he used, how much force he used to push his body with his legs. I don't know, those are measurements. So we measure. And we're saying that the measurement is a physical object? Hopefully not. Hopefully the horse is the physical object. And he's a physical object before we measure what he did. And the physical object is not the horse plus the distance he covered. The horse is the object, not horse plus distance. Horse plus distance is not an object. Like, moving boy is not an object. Boy is an object. Moving boy is not an object. It's a movie. And, I couldn't convince him of that. He insisted that measurement is what an object is, that which you can measure. And so, I need to cover that in a little bit of detail. I have to modify my article only because of this input, which was unexpected for me. And I think what people do, they try to protect their religion by putting some of these definitions that are convenient for them. Of course, they throw that at me and say, well, the one you're using is convenient for you. Well, I'm trying to be objective. I'm not trying to protect the religion. I'm trying to say that, in order to do physics in a rational way, you must have an object, and an object is that which has shape. And an object is a standalone object, and if there's nothing else in the universe, and there's a table there, well, that's an object. You don't have to see the table move, because movement would require, comparison against something else, another object. And here you only have one object. Measurement, same thing. If you're going to measure with respect to what? To a tape, to a scale. Against what are you going to measure? You got to measure it against something else. You have to have some kind of standard, okay, in order to measure something. And so again, hopefully a table does not need to move or do anything for it to be an object. And of course, it's got to be a standalone object. You can't have a field as an object, because the field is not a standalone thing, right? It requires a magnetic field. For example, we can't see the magnetic field without the magnet. And you can't have a gravitational field without, the sun or the earth or some other object. So again, it's got to be a standalone thing, and I don't think there's any measurement involved. And part of it has to do with the fact that measurement itself is motion. And as I said to my brother, I said, hopefully an object, or you have to define object before you define motion. And if measuring, stretching out the tape, whatever you do, or timing, or whatever you do, however you measure something, requires motion. Measurement requires something to move, whether it's unrolling the tape, running the clock, pressing down on the scale, whatever you do, or counting, atoms, because that's also, mass, you could say, quantity of matter. Well, you got to be counting all these atoms, right? And so all of it involves motion. And I think that's where the definition of measurement fails. Those are some of the ideas I put forth, and I just got them thinking, but not conceding. So get ready for some of the things that people say out there. Obviously, a mathematician's always going to say measurement because he likes that. He wants to put a unit, time, seconds, weight. He wants to put kilograms in there, mass, same kilograms or number of atoms. He wants to put some kind of unit in there. And so if you take that away from him, you kill his whole argument, his whole religion. And that's why they're going to fight till the end for measurement. Anyways, we need to have an object to do physics. We need to define what we mean by an object. And the first realization, for those who've done a little bit of research on this, or you can do it starting today, you'll find that no one in the last 10,000 years has defined what an object is for the purposes of science, for the purposes of physics. And this is stunning, because if our first principle holds and we say you can't do physics without an object, you would think that in 10,000 years someone would have realized this and said, oh, hold it, let's define what an object is. And no one's ever even realized the importance of defining what an object is for the purposes of physics. More so in the last 400 years, since the alleged scientific revolution that started in the 17th century, days of Galileo, Newton, and Huygens, and all these other people. So the issue here is that, no one has realized that, and that shows you the state of physics today. If no one has, obviously no one cares about physical objects. And I'm not only talking about people of the 20th century, which obviously have forgotten about objects altogether. They're doing concepts completely, 100% concepts. But I'm talking about people who seem to care or look for causes and mechanism. People like Michael Faraday, people like Augustin Fresnel in France. These people wanted to get to the bottom. They said, what is it that's moving in there? What is this light thing? What is this magnetic thing that's between two magnets? What is electricity? They wanted to know what's. And that got lost with quantum. Nobody worries about the what's anymore. Nobody cares about what gravity is anymore. And they can live with space time. We got the word time in there, which is a concept. They don't care. They just bend it. And so we have a problem with that because uh, we have lost touch with physical objects. We don't use physical objects to do physics, and I'm talking about the mathematical establishment. But you wonder why the people who did care about finding causes and mechanism, people like Faraday and Fresnel and Huygens and so on, all these people, they did realize that you need some kind of object. Newton himself said, "Fingo non hypothesis." I have no hypothesis. He did ponder these issues. He did wonder, how does gravity actually, what is the mechanism? He had the equation, no doubt about that. He had the relations, but he said, what is doing this? How is the Earth being pulled towards the sun? How is the moon pulled towards the Earth? And he realized, that the equation was correct, but he had no mechanism for that, and that's why he said that. I have no hypothesis. But at least he was conscious that this had to be studied and looked into. And today, we've lost that completely. Anyways, for a physical interpretation, you need a physical object. You cannot do physical, and I'll emphasize physical, you cannot do physical interpretations with concepts. You cannot say you're going to move love around or information. You cannot transfer information or kick, love or grace or intelligence. You can't do physics by moving concepts. And that's the bottom line. So once we define the word object as that which has shape, now we have something that we can use in physics and in science, right, in general. And one of those is the fact that, again, if you're going to be trying to give a physical interpretation to things such as gravity or magnetism, you got to put a little object in there. And yes, if you just talk about measurement, or for that matter, that which you can touch or see, or mass, or that which moves, or volume, well, then you're dealing with concepts. But if you got to put an object there, you say, well, what object am I going to put in there? Well, that's where you have to use your imagination and see what you can put in all these instances that makes the universe work. And you can't put particle, and you can't put waves. And the reason for that, the main reason, number one reason, okay, is that you cannot produce attraction, the force of pull, with particles or waves. And the reason for that is that, these are one-way mechanisms. Particles go outwards. Waves go outwards, only in one direction. And that's why you can't use these. You cannot try to do light. Light, maybe you can get away with particles if you say, okay, it just goes out, fine. Okay, maybe you can get away with simulating light with one-way mechanisms. But you certainly cannot do pull. You cannot do gravity with one-way mechanisms. You need some kind of two-way agent in there. And so, this is where mathematical physics runs into trouble, and that's where they put concepts instead of objects. So that's what the first presentation was about physical interpretations. In order to do physical interpretation, you need a physical object. And an object cannot be measurement, as my dear brother said. No, it's got to be something which has shape. And what are we saying here? I'm saying that you got to make the invisible visible. And again, when I blow a piece of paper, you don't see the air, but hopefully when I give the explanation of what moved the paper, I, make the invisible, the air in there, I'll make it visible for you so that you can understand my theory of what moved the paper. And we got to do exactly the same thing when we look at gravity, when we look at electricity, when we look at magnetism, the functioning of an atom. All of these things have to be mediated by some physical object. And all you got to do, if an object is that which has shape, all you got to do is make it visible. Very simple. And of course, mathematicians are not used to doing that because they just like to describe and say, look, this is what we measured. This is the value that I get. So many seconds, or so many kilograms, or so many meters, whatever. And that's why they got into doing only concepts. Okay. So when I finished that, I moved on to the Slit Experiment, which was the second part of my or the second presentation. Actually, all these were somewhat separate. They relied a little bit one on each other. One was a prerequisite for the following one. Slit Experiment. What was the Slit Experiment? Slit Experiment says that, well, let me put something up here. Again, we can't do it with one-way mechanisms. That's the first one that I want to make clear. And here you have one-way mechanisms. You got a stream of particles, and you have the plane transverse electromagnetic waves, whatever waves are, but let's assume they're a physical object. Those little arrows there that you see, those are really vectors. They have magnitude and direction. That's what the arrow stands for. It's not a physical arrow. It's each one of those arrows is a pictorial representation of magnitude and direction. That's all it is. And as you can see, they're all 90 degrees to the flow, and that's why it's called a transverse wave, because the vectors for these, the magnitudes and increasing and decreasing, this wavy thing that's in there is essentially moving or extending, or I guess it's moving perpendicular to the flow of light. Okay, so what's the problem? Both of them, as you can see, are one-way mechanisms. The stream of particles in this case are moving to my right, and the electromagnetic wave is also moving to the right. The idea here is that whether particles or waves, they have origin in the atom. Okay, so they move outwards. They can only move outwards. And obviously they receive from other atoms, but it's another set of particles, another set of waves. It's not the same wave that's leaving. Okay, so waves, it's only one-way mechanisms. Okay, so what's the issue here? The issue is that we have the Slit Experiment with particles, and the way they typically illustrate the theory is that the particle bounces off the edge of the slit. Okay, we'll call it the window to make it simple. So we have the window of the slit, right? And the particle hits there and goes inwards and interferes with particles coming from the other slit. So they bounce when the two particles meet. If they're in phase, whatever that could mean in terms of particles, you have a bright man. Wherever they're off by half a wave, I don't know how you can interpret that in terms of particles, but let's assume you could. If they're off by half a diameter, the radius is slightly off, whatever. I don't know how you can, maybe the tennis ball, one tennis ball is half a diameter away from the other one. That's the phase difference. Well, then you have a dark band, okay? And that's how they explain it. And same thing with, here we have, I thought I had, oh no, I don't have it with waves, because waves is the same thing. Essentially what they're saying is that the wave hits the slit, and when the wave hits something, whatever it hits, it instantly collapses. It's called a Wavefunction Collapse. What does that mean? It turns into a particle. But in the case of wave, when they do the Slit Experiment, they like to explain it with water. The analogy is always with water. They say, look, what happens when water goes through some kind of opening? We'll call it a slit. Okay, so you got a little opening, water goes through there. Well, water tends to open up. And so when it hits the slit, whether it's got that little top part in there or not, they say, well, as soon as it touches the slit, it immediately on the other side of the partition of the slit, it opens up and it goes in every direction. And that's how they simulate, or that's how they explain, or that's how they model this thing, and try to convince you that the wave can go inwards. In other words, around the center of the slit. And it's cheating because you can only get that effect. As far as I know, the only way you can get that effect is if it goes through a slit. But if you have the opening, if you just have a tree, it tends to go outwards. But yeah, it goes around, I guess. But here's the point. The point that I'm trying to make here is the following. Here, if you remove the edges of the slit, in other words, if you just remove that part there that's disappearing, well, the particle should go straight, and so should a wave. If it's an electromagnetic wave and it goes in one direction only, it should just go straight, should not touch anything. And for some reason, the wave goes around, and that's why they like to use water waves, because they say, well, on the other side of that tree that you've got in the middle there, the wave does go around and goes inwards. Okay, with water waves, you can probably simulate that, but the question is, does light behave as water waves? Is that a fair analogy? And I'm saying it's not, but let's continue here. What's the difference with the rope model? Well, the rope is a two-way mechanism. As you can see, the rope just twirls in place. It's already stuck to the other end, so it doesn't leave whatever origin it has. It's stuck to both ends. It just twirls in place, and so the wave, the torsion, goes in both directions. And that's the advantage of the rope model. One guy, I can't remember who it was, says the wave arrives before it leaves, or arrives at the same time as it leaves. It's just like, that's the description they try to give you of how light behaves. And yeah, that's exactly what a rope does. A rope twirls in place, so it's leaving and arriving at the same time at both ends. There should be no question about that. It just twirls in place. Okay, so what do we have here? We have the slit model of the rope model of the slit, and that's that you have the ropes already connected to the needle and to the screen, both. Okay. And before you turn the light on, what you have is simply they're already tied. They're just at a frequency that our eyes cannot pick up. As soon as you turn the light on, you get the fringes instantly, almost. For the speed, for such short distances, 300,000 kilometers per second is quite fast. That's a torsion. That's the speed of the torsion. So as soon as you turn the light on, you go blink. For us, it's instantaneous. But now we can explain why, because the ropes are already connected there. They're already, the highway is there. And all you need to run this car through the highway, and this car runs at 300,000 kilometers per second. 300,000 kilometers per second. That's almost the distance from here to the moon in 1 second. And it does so for a few meters that you have in your room wherever you do the experiment. So it's instantaneous for us. So as soon as you turn the light on, now the ropes start twirling at a higher frequency, and where you have rope meets rope from one side of the slit with one from the other side, if they're in phase, you get bright band, and when they're half a link away from each other, they're out of phase, that's where you get the dark band. And I didn't invent that, by the way. I only got the rope model to do it, but this is what you see. You can, they've been doing this with waves for a long time. What we're doing is replacing the wave with the rope, and we're saying with the rope, it makes sense. Assuming the pink one there, the pink thread, it ends up in the same position as the one coming from the other side of the slit. If they're both in phase, then there's constructive interference, and when have a green one against a pink one, well, then you're out of phase. Okay, and that's when you have destructive interference. And I explain that in a little more detail, not only in the presentation, but also in the paper that I'm finishing writing. Here's the needle experiment, which I like to show because, here you have the needle. Here it is. Okay, you have a needle, and you shine a laser, laser pointer, and you can do this at home, not a $1 billion experiment. Just put the needle, like I did at the presentation, and you point the needle. Let's see. That was great. Okay, anyways, you can point this at a wall, whatever, and you'll see that the fringes. You will see the fringes created by the needle, the laser pointer, monochromatic light, by the way, light of a single frequency, and a single wavelength, and a needle. Okay, and all you have to do is just point it at the wall, and you'll see what I'm showing there. You'll see the fringes. And again, this experiment was done first by Newton, by the way, and a lot of people were not aware of that. One guy who was aware of it was Thomas Young. Thomas Young, 1801, he does this experiment after reading Newton's book, Optics, and Newton covers it in his book, and he says he saw shadows. So Thomas Young repeated the experiment. He was doing different experiments. He did the double slit, and then he said, I'm going to try Newton's experiment. He did so, and he found the fringes. And he wrote about that, and that's what I presented, in Buenos Aires. And so I decided to, I don't know why that got stuck in history. I unburied it, unearthed it, and decided to do it myself. And yes, you can see there, you get the fringes. Those are caused by the needle. And so now we got a problem because, again, as you can see here, where is it? With the particles, if you put a needle there, the particles should just go straight. So you cannot explain this with quantum. Remember, quantum is a particle theory. They insert the wave to save their hides or skins, but really the wave has no business in quantum because quantum is a particle theory. And what they try to do is put the wave whenever they can't explain something with a particle. And here you see it's got nothing to bounce against. So if you can produce a fringe with particles, well, you got to explain how that happens. You got to rationalize that, and that's something they can't do. So with a needle you can't do it with a wave either. But again, they have the wave going around, and but here we have a problem with that because look at this. Here you have this is a ripple tank, and the waves are coming from above. They're going through two slits there and out the other end. Here's the single slit, okay, and it's a very narrow one. Here's a little wider slit, but you can see the waves at the bottom just go outwards. They don't interfere. Here they interfere because you got two slits. So let's look at that one more time. Here you have a single slit, very narrow single slit, okay? And you can see the wave is not interfering with anything. It just opens up. It just fans outwards. And here the same thing with a wider slit. You can see that it's always going outwards. It's when two slits are there that one wave interferes with the other one. So how do we explain this with the same mechanism with particles? You can't, because with a single slit, the particles, assuming they went through that little hole, okay, they would open up. Okay, they would just get wider and wider, and with the two slits there, you would have particles interfering with particles. But why would they? How do you explain this? How do you explain the mechanism with particles? And they don't. What they do, they explain it with water waves. And the question is again whether light behaves like water waves. And I guess the answer to that question is no, it doesn't. Okay, so that's essentially what we discussed for the slit experiment. You got to read the paper. You got to look at the video I'm going to upload hopefully this week. I'm working on that right now. And well, then I'm sure lots of people will have questions about that, of how that's really done. From there, we moved on to polarization, the third leg of the presentation, or the third presentation. They were kind of individual. One was simply a prerequisite to the other. Why is the slit in a prerequisite to polarization? Because I think that you do also have a little bit of this phenomenon, of this mechanism, inserted into polarization. And again, once you read the paper, you'll see how I put that in there. But there's a bigger mechanism as far as I'm concerned with polarization. Let's start with what it is. Polarization, here we have it. Polarization, okay, you shine a light. I'll move aside a little bit here. You shine a light, monochromatic light. Well, no, I'm sorry. You shine you can shine any light, essentially. As far as I'm concerned, you can shine any light, yeah. And what happens is the polarizing plate, calcspar, Iceland calcspar is famous for this. They've got their arrays oriented. And in this case, we have the arrays for the first polarizer vertically, and for the second polarizer, they're horizontal. Okay? And supposedly, if we follow Mr. Fresnel, who came up with a picket fence explanation, here you have it, goes something like this. Let's see, let me make that a little bigger. Goes something like this. The first polarizer allows the vertical component of light, and they usually explain that by saying it's the electric field. Okay? And so you had electromagnetic, this is the electric component, and supposedly what goes after that is just the electric component of light. So it's like light that's in between these two polarizers, the vertical and the horizontal, allegedly consists only of the electric field. There is no magnetic field because that's what's stopped by the first polarizer, allegedly. But they'll say that, you have lights in all these different directions. They don't like to look at a single wave. They would like to show you that, there's many waves, and so they chop off the electric from one and the magnetic from another, and they build a wave again, I guess, on the other side. I don't know. Because if they're going to chop just the electric field, are they saying that the light between the two polarizers consists of only electric field? If they chop off the magnetic field? Okay, but anyways, the deal is that you have a horizontal and a vertical component. The vertical polarizer does not allow the horizontal component of light to go through, just the vertical ones. And then when you turn the other polarizer, here you have, they're both like this, right? Let's see if I got it right. And then the second one, you turn horizontal, you have 90 degrees. And what happens? It blocks the remaining vertical component, which is the one that made it through. And that's why you see no light on the screen. That's the explanation. How does that differ from what the rope model proposes? Well, the rope model says that instead of going through the holes, the interstices, the spaces between atoms, the rope model says light goes to the atom and through the atom. Light is relayed from atom to atom. Not through the holes, not through the spaces between atoms, but from atom to atom, because all atoms are interconnected. And so it's a totally different mechanism. So how do we produce this effect? Well, something similar, and this is what I showed. Again, $1 million experiment here, so treat it very well. Let me get this out of the way so that you can see it better. And it goes something like this. Here you have light, and let's assume you got these ropes, okay? You see them there? Okay, so we have the ropes, this way. You have the ropes straight ahead, okay? What happens when you turn the second polarizer at 90 degrees? Well, you get that situation with the ropes. Okay, now you don't have them connected straight ahead, but you have them, you go from here to there. That's essentially the main mechanism for why light is stopped. It's not relayed. So one of the questions came up, and for you to ponder. Okay, so what happens when we turn it one more time? So now we have them like that, right? Again, they're not straight ahead, but now we've got the beam back again. So when it was like that, we can all understand why light goes straight ahead. Here we can say, okay, now light is stopped. Fine, so far so good. But when we turn it one more time, well, we're not straight ahead. So why does light get reinstated? Why can we see light again when we're 180 degrees from where we were? Here's 0 degrees, here's 90 degrees, here's 180 degrees. We have to explain that. And of course, there is an explanation, and all I can ask you is to read the paper when I put it out there. I'm going to put the video and the paper out there. There is an explanation, and for this you need to look at the molecules. Okay, you need to know what the structure of the molecules are in the calc spar. Okay. And no one's done that. No one's really done, well, they've done a little bit of that, but it's they just described it. They said, well, when the molecule is like this, light doesn't go through, and the molecule is like that, it does go through. But they don't explain why, what's causing, what the mechanism is. And I'm going to work on a mechanism in the papers. So that's as far as I can give you right now, simple. Straightforward of why the second polarizer stops light. That's just a stopgap until you read the paper. Okay, I'll let you try to figure out. I mean, obviously you want to try to figure out in your own brain how that could happen. I can only give you my version. And again, I don't urge you to believe it. I urge you to understand it only. And then meanwhile, you can work your own mechanism. See if you can come up with a better mousetrap. Maybe you got a better solution than I do. Keep in mind one thing that's always important also, and I didn't get the image, but when you, well, I got it here, hold it. Let's see, I've got it here. See, I made a second plate here. Okay, and the issue is that when the second polar, the one in the middle, right, if I insert a 45 degree angled polarizer in the center, in between the two plates, like this, see here? This one is 90 degrees, this one over here, right, to this one, right? But the middle one, as you can see, is 45 degrees, okay? That's important to note. And when you put that 45 degree angled polarizer, you reestablish the beam. More precisely, as you move that second polarizer between these two polarizers, as you move them gradually from 0 to 45, you recreate more and more and more of the beam. So it's a gradual appearance of the beam. It's not like you got to wait till you get to 45 before you reestablish the beam. You're reestablishing the beam for every angle you turn that second polarizer. Here it is again, okay? So you have, you start out like that, right? Just look at the two outer ones, right? And if you just turn this one around, and here, let's do it that way. If you turn, let me get that right. If you turn this one like that, right? Then you can see what's happening to the ropes. The question is why, when you put a third polarizer between them at 45 degree angle, right? 45 degree angle, why does that reestablish the beam? Okay, and that's what we need to explain. That's what the papers are going to be explaining. Okay. Anyways, just thought I'd give you a quick rundown of what we did in Buenos Aires. Besides eat and have fun, we did enjoy ourselves. I think we had a good discussion there with the folk that went there, and I can only urge you to assist, attend the next one if we do that one in Sweden. And some questions will pop up of, how some of these things, the mechanism behind these things. Hopefully we can address those issues. Read the papers and watch the videos. And I'm also going to make a little real physics simulation of both the slit and polarizers. Hopefully for that you can see the mechanism. Mechanisms should be straightforward, easy. You should look and say, okay, I understand the mechanism. That's how physics should be. Physics is for kids. You don't need any math to understand this stuff. All you need to do is visualize the mechanism and say, oh, okay, I see how Mother Nature does this. And if the rope model has any validity, we should be able to do it that simple with some kind of rope model. Where you use the rope as the mediator for light. You should be able to explain polarization, slit, and the whole works. You can't just say, well, I explained this experiment, and you still cannot explain none of the rest. Of course, there's a lot of stuff out there. I can explain magnetic attraction between two rectangular magnets, but then some people say, well, how about levitation? You've seen probably out there, this magnet floating seemingly in midair because it's pushed up there by another magnet. And people say, well, how does that? Well, first let's understand the simple stuff. Then we can always work on the complex stuff. And this is where we run into trouble. People first want to jump into the one that's awesome, the one that really awed them. Say, how is that done? Well, let's get simple first. Let's find out how a simple one works. And then you can progress and say, okay, now I know how this one works. Let's see if we can apply that same mechanism to these more complex situations. Okay, folks. Anyways, once again, we're going to be having these lectures Sundays and Wednesdays, 2 times a week. Give you time to give some feedback. Also give us time to catch up on a lot of stuff that we got to do. And I've got Hans is my son. He's going to be in Buenos Aires a couple months down there, and he's probably going to participate here and there. He's got a lot of work to do, doing some programming stuff, and so he will be participating on and off. Hopefully I get to see him every now and then, and you will be able to hear him as well, or at least maybe he'll type something whenever he's attending the lectures. What else? Well, I guess that's it. All I want to say is, those who missed it, well, they missed a lot of fun that we had, and I guess that was worth it to go down there and discuss things with some of the folk, and eat and be merry and drink merry. We had some beer, and we had some good food and good chats, and hopefully we repeat that next year if we do this in Sweden. Okay, with that, I'm going to see you on Sunday, and hopefully we can see each other, Sunday at 9 o'clock, Frankfurt time. What else? I guess that's it. Unless anyone has any questions, all I can urge you is to read the papers, watch the videos, and after that you'll probably have even more questions. We'll see you on Sunday. See you then. Bye-bye.